Electron affinity is energy associated with gaining electrons by an atom in a gaseous state. So whereas ionization is focused on pulling that electron off, electron affinity is associated with gaining that electron. So when we talk about fluorine needing that one electron, right? That would be a very exothermic, like that is going to be a high electron affinity because fluorine really wants that one electron, high electron affinity. Low electron affinity would be sodium. Ever seen sodium minus? Nah. Sodium does not want that electron. What will it do with it? Now it will be like sodium minus, and now it has to get rid of 2 electrons in order to be full. Sodium does not want this. This would be super low. Low electron affinity. It does not want it. This is super high. Okay? So electron affinity is gaining electrons. So therefore, left to right on the periodic table, electron affinity increases. Now, as it increases, it gets more negative. And it gets more negative because it is exothermative. And it increases because the Z effectiveness. The number of protons in nucleus increases, but the energy level stays the same. This is the kind of answer they're looking for. It's important to note, I am not relating this to the periodic table. I am not saying the reason that fluorine has a higher electron affinity than sodium is because it's farther to the right on the periodic table. That is not going to work. The reason is because it is in the same, the electrons are in the same energy level and the nuclear charge is greater. That is why. So the electrons are pulled more tightly into the nucleus of fluorine than they are to to lithium, which has the same energy level. Okay. All right. Top to bottom, those atoms are getting larger. Those valence electrons are getting farther away. So what's happening to the electron affinity? Is it increasing or decreasing? It's decreasing. So it's decreasing because the draw to those energy levels is decreasing. Top to bottom, decreasing. And we can say it is becoming more positive. And that is because we are adding energy levels. So the electrons are getting farther from the nucleus. Does this make sense in terms of force of attraction? I hope so. Okay, metallic character. This is kind of a strange trend because they're, it's kind of a weird trend because we do use the periodic table in this trend, so we don't really talk about, especially in honors. Non-metals are on the right. Metals are on the left. Left to right, this metallic properties decrease. Elements that lose electrons easily are on the left. And those are metals. And elements that gain electrons are on the right. And those are nonmetals. And then other metallic properties exhibit the same thing. Top to bottom, metallic properties increase, but it's not really consistent. So, for example, that would be like tin and lead. Are at the bottom of their families. But at the same time, tin and lead are way over to the right. So this is not like, it's just not a very good trend. That's why we don't talk about it much. Mostly, I think the trend here is that the metals are on the left and the non-metals are on the right. So it's not a trend that you're going to see in a question of like, put these four in the most metallic, like with ionization energy. There's no periodic table with numbers attached to it kind of thing. It's more along the lines of metals are on the left, non-metals are on the right, metallic properties are more to the bottom than the top. Which you can see if you look at gases, they're kind of like pushed up more to the top than to the bottom, that kind of thing. Okay? Binding energy. Okay, so just a little bit of a brief explanation. So binding energy is the amount of energy, it's very confusing, I'm telling you right now. The amount of energy required to remove a particle from a system of particles. So the binding energy for the first valence electron, the first one only, is equal to the ionization energy 1, the first ionization energy. After that, the greater the number of protons, the greater the binding energy. The reason is because the binding energy, as you pull off the ionization, as you pull off an electron, the binding energy has to do with the number of protons. And the binding energy is all of these electrons. It's all of them. And so when you pull off one electron, it is equal to the ionization energy. But after that, it's all different. And the binding energy generally is greater than the ionization energies. So they're going to talk a little bit about that, but I think that the comparison is one of those vague things because I looked at many different sites and they all had the exact same wording definitions, the exact same words. I could not find other worded definitions so that I could like explain in different words, and the wording definition was not a valid explanation. They just kept saying like the same thing over and over and over again. So I think it's a very vague concept. I think it depends on whether you're in physics or whether you're in chemistry. So there's two different concepts there. So I think that what I'm learning is if it's a vague concept, then it's a concept rather than a calculation. That's what I'm starting to learn. So let's look at this chart, which is what you're going to actually see on the test. And I think that's what we have to look at. You'll notice that there are peaks here and that these peaks here are the same size, and then these peaks here are 3 times that size. So this peak should be, this tall. No, sorry, nope, that's right, 3s2. This should be a 2, not a 1. So these peaks are S2. See that? So this is where the 1s2 is. This is where the 2s2 is, and this is where the 3s2 is. And then these are 3 times that tall because they represent the number of electrons. All right? And so I think this is electrons. Sorry, cross out atoms. This is electrons. There you go. So this is millijoules per mole it's going to take to pull them off. And you'll notice the ones closest to the nucleus, and you can write that here, that like it's sort of like the nucleus is over here, but it's not. It's just a graphic representation. So the nucleus is here, then the 1s2, then the 2s2, then the 2p6. See how this is? Because these are not labeled on the graph. Important to note. I labeled these. They are not labeled on the graph. So when you see this graph, you have to kind of like look and you have to judge how tall are these, right? All right, and then you have to judge how many electrons they are because they're going to say, what element is it? So you have to say, oh, 1s2, 2s2, 2p6, 3s2, 3p6, it's argon. But if it looked like this, well, that's twice as high. So now I'm looking at 1s2, 2s2, 2p4. Oh, that's oxygen. Get it? Now, why is this number so much lower than this? Because the binding energy is lower. This one, Coulomb's law. It's closer to the nucleus, so it's going to take more energy to pull it off. These are, according to Coulomb's law. So, binding energy increases left to right because the increase in nuclear charge. Well, that makes sense because look, we're talking about pulling off these electrons. So just like the ionization energy, if this nuclear charge increase, it's going to take more energy to pull these off, right? But then also going top to bottom, here's the weird part. It increases, not decreases, due to more protons in the nucleus. Because we're not talking about pulling off the outermost. We're talking about pulling off all of them. So that's why it takes more. Okay? Well, when it talks particles, it's talking about any particles, but in this case, we're talking about electrons. Yes. Okay? So the ionization is removing only the first. First you remove the first, and then there's a second ionization energy. It's basically the definition of the ionization energy is the most loosely attached particle. So first, there's a first ionization energy. When that one's gone, you look at the next loosely attached particle. The binding energy is basically, what's the binding energy of this one? What's the binding energy of this one? So you can pick an electron and get the binding energy of that electron. And the binding energy of them increases when you have more protons, right? The ionization energy is what it is because you're only pulling off the last electron. That's all. Okay? All right. So we don't have time to do the videos. Tomorrow when we come in, we're going to do a quick review. This is the last of the notes for this chapter. We're going to do a quick review, then we're going to watch those, and then you're going to have homework on the whole chapter. And when we finish this chapter, we're going to do the first Unit 1 progress thing with all the questions. All right? Yep. Completion. But I'm hoping that it's going to, yeah, I'm pretty sure. Yeah. Yeah, like I've been through it twice and I'm feeling pretty good about it. Yeah. But we'll do it after the test.
Wait, what? We're doing the progress check after the test?
Yep, because it's the whole unit. And we're not doing a unit test. Yeah. We're focusing on this test, and then we're gonna do the progress test, and I'm hoping that you guys are gonna go, oh, totally, like, we have Unit 1 done, and look at where we are. We've already finished almost all of Unit 6, almost all of Unit 4, half of Unit 3. So we're doing really well, but we've completed this binding energy. We have completely completed Unit 1. So we're going to take that progress check. We're done with that. We're moving on. We're going to take the Unit 4 test probably after this next unit. So we're kind of like moving along. Yeah, we're not too bad off. I'm hoping, I had hoped for chapter 10, but now I'm kind of hoping for chapter 12 by Christmas. So we're, moving right along. So I think we're doing okay.